All right, this is part 3, the last part regarding symmetry for E&M, electricity magnetism, a little bit about submarine signals, conservation, laws, and parity. And in part 1, we looked at the symmetry for E&M problems. And we did 2 cases. One was for a uniform line charge, infinitely long line charge. And using symmetry operations, we found that the electric field was radially outward. So for something with that kind of shape, you would probably use cylindrical coordinates. So I'm indicating E rho hat for radially outward. And if the charge was negative, then it would be radially inward. And looking along the length of the wire, you would see the field going radially outward. Or again, if the charge is different, it would be going inward. So that was one of the symmetry things we did in E&M to get to that. The other one was we had an infinitely long wire carrying a current I, and we found out that the field was circular around the wire. So if you looked along the length of the wire, you'd see the magnetic field pointing around, tangent to a circle. So again, in cylindrical coordinates, I'm indicating that as a V component. So that was part 1. In part 2, we continued on with the symmetry for E&M, but we applied it to a submarine. Very simple approximation. This is not exact. And what we looked at was the 3D radio current from a point. So we imagine a point in space in some kind of a conducting medium, and the current is flowing out radially in all directions. I can't show it coming out of the board or going into the board, but I hope you get the picture. And the magnetic field from that was 0. So then what we said, okay, let's take that and imagine that the current goes all the way out to infinity and comes back to some other point. And these 2 points are now spaced a distance L apart. And what we said this represents, again, approximately, is a corrosion current for different metals in seawater. And I'll get to an example soon of a submarine hull, and a prop. So here the current's flowing out, here it's flowing in. And we imagine the source of the current to be a battery in between them, which is insulated from the conducting medium. And that causes a electric current moment to exist. Which is equal to the current flowing and the length, IL. Again, we're looking at that as an approximation to one metal here, a different metal here, in an electrolytic solution. They're corroding, a corrosion current is flowing, and we're connecting one with the other with a insulated wire of some sort. And we took this idea and applied it to the case of a submarine. Submarine has a different metal for the hull than it does for the propeller. We're associating the green here, and black here for the different metals. And I don't know if I have the current direction correct, but that's not important here. So a submarine will have that electric current moment. Submarine will also have a magnetization from the steel hull. And if you fly over the ocean with an aircraft equipped with a magnetometer, you will see a magnetic field from the submarine consisting of the magnetization and this electric current moment. And again, this electric current moment here is a corrosion current between the hull and the propeller on the submarine. So that takes care of, that's a quick review of part 1 and part 2. We now want to go to part 3. And in part 3, we're going to be talking about conservation laws and parity. So to start that off, in 1917, Emmy Noether came up with a remarkable theorem. And the theorem basically says that if you have symmetries, you have conservation laws. And some of the examples are symmetries of translation in time. That corresponds to a conservation law, conservation of energy. Rotational symmetries, conservation of angular momentum. Translations in coordinates corresponds to conservation of linear momentum. And then you can get to more complicated things, gauge transformations, conservation of charge. This is heavy stuff. I vaguely remember a quote from Albert Einstein saying how important her work was to his work. I can't recall the exact quote. But again, this is heavy stuff, and when you have heavy stuff, it's fun to do something different. So I want to add my own conservation law. And the one that I would say is knowing and not knowing. And that corresponds to nature's greatest law, conservation of confusion. So, okay, that's just having a little fun with something, all right? Now the question comes about is parity conserved? And what is parity? That's where we're heading now. And to do that, we'll point out that physical laws are ambidextrous. If the board was a mirror and I looked with my hand in the mirror, I would see a left hand looking out at me. A mirrored view of anything you can see is a valid event in the universe. And that's what we mean by parity. So parity is physical laws are ambidextrous, and a mirrored view of anything is a valid event in the universe. Now, parity is conserved in E&M, electricity and magnetism, and that's what we demonstrated back when we did those examples in part 1 and part 2 in a sense. It's also conserved in strong interactions. We're not going to talk about strong interactions. But it is not conserved in weak interactions. And back in the 50s, Li and Yang formulated a test regarding parity. And a lady by the name of Wu, she performed the test. And Li and Yang actually got the Nobel Prize in 57 for their work, and Wu did the test in 1956. And what I want to do now is I want to talk about, in a very simple way, what Wu did and how that shows you that parity is not conserved when it comes to the weak interactions. So if we look at the periodic table, here's cobalt. And Wu did her work with the element cobalt. A neutron is added to cobalt to make it radioactive, and it decays to nickel. And so what we're going to do now is go into a little bit of the details of that process. So we start out with cobalt. And if you excuse me while I erase the board. So once again, there are a number of things that are conserved, and a very interesting question was asked about parity in weak interactions. And it was truly a remarkable experiment on the part of Wu to get the results that she did. And it surprised a lot of people, made some people happy, made others not so happy. because now we seem to have a violation of what seemed to be an expected process, conservation of parity. So we're going to start out with cobalt, and cobalt is element 27, and the naturally occurring is 59. So we have cobalt 27. And what we're going to do, and the details of how this is done is not important, we're going to add a neutron to it. No charge, mass 1. And that will result in cobalt 27, 0 plus 27, and 60. So now we have cobalt 60. This is the material Wu used. Cobalt 60 is radioactive. It's going to decay into nickel. And it decays by beta particle emission. So we get an electron. And also neutrinos, a neutrino, an anti-neutrino, anti-electron neutrino. The electron decay is going to give us a proton. So this will become 28 now for nickel. And it'll be nickel 60. And this will be minus 1 and 0 mass. So we have 27 is equal to 28 minus 1, and 60 is equal to 60 plus 0. The other thing that comes out of this, the nickel is the nickel nucleus is in an excited state. So there are a couple gamma rays that come off, and they are in the mega electron volt range. But we are not going to worry about the gamma rays, but I want you to know that they're there. So this is what happens, but it really doesn't tell you where the weak force is. So there's a couple of ways of looking at this. And we'll look at this neutron that changes by giving off an electron, and so now we have a proton left. So basically what we have is a neutron going to form a proton plus an electron plus the anti-neutrino. This can be written so that you can see the weak interaction by showing that there is an intermediate state involving a negatively charged vector boson that we indicate like so. And then this will go to give us the electron plus the neutrino. So this is a way of trying to show you that with cobalt 60 going to nickel, that there is a mediator of the weak interaction occurring with this negatively charged vector boson. I think everybody's familiar with cobalt blue. That's that compound cobalt aluminate, that nice glassy blue color. Anyhow, one of the other ways to look at that, if you like Feynman diagrams, we're going to draw a Feynman diagram now with time going up. So in comes the neutron. We'll label it the neutron. Out goes the proton. And then we show with a squiggly line and an arrow the mediator, the negatively charged vector boson. And that then goes to the electron and the anti-neutrino. But here is the real thing to look at. Let's say that's the nucleus of cobalt 60. Let's say that it has a magnetic moment with a north pole here and a south pole here, and it's rotating in this direction. What Wu found was that when the beta decay takes place, the electron comes out this way. So now the trick is, or the step is, to take a look at how this would appear in a mirror. So here's our mirror. And we're going to look at that in the mirror. What would we see? The magnetic moment here is a pseudo-vector, so it transforms differently than real vectors do. If my arm is a real vector, I look in the mirror, say the board's the mirror, and I look in the board, I see my arm pointing in the same direction. A pseudo-vector is opposite. So in a mirror, we would see the magnetic moment pointing down. So this would be the north pole, this would be the south pole, roughly speaking. And now the rotation would be this way, also a pseudo-vector for the angular momentum. And the question is, which way does the electron come out? We're showing over here that the electron came out of opposite to the moment direction. When we do this reflection into the mirror, it'll be in this direction. However, that is never, or that's not what generally happens. So the reflection is violated. So parity is not conserved. Another interesting aspect of this is with the neutrino. The anti-neutrino is right-handed. So the spin and the velocity are in right-hand direction. The neutrino is left-handed. That's also buried in the details here. And sometimes you hear the fact that there are no left-handed electron neutrinos, and there are no right-handed neutrinos. And that is kind of like one hand clapping. So it was this experiment that Wu did that showed that parity is not conserved. This is what you would have expected, but this is not observed. And the way she did this was by cooling cobalt 60 down to close to absolute zero and having a magnetic field to polarize the cobalt nuclei in a particular direction. So parity is not conserved for the weak interaction.